Welcome back to the Physical Sciences section, and we carry on with rates of reaction. When we look at what we've dealt with previously, we looked at the macroscopic view, meaning what we can observe, what we can see, the changes in temperatures, the changes in color. We looked at the macroscopic view, and we linked that to the factors affecting the rate of a chemical reaction. We then also looked at the ways, macroscopically, the ways that we use experimentally to work out the rate of reactions. We also touched on the different graphs that we get when we do that. What we are going to do now is we are going to look at the submicro view or the microscopic view, where we cannot see it, but what actually happens on a particle level. So, as I said, macroscopic view is what we can observe, what we can see during a reaction. We can see if we use a thermometer, there's a temperature change. We can see that there's a color change, like with the sulfur, and we can see or feel if something is getting hotter or colder. But on a submicro view or a microscopic view, we're actually looking at things that we cannot see, but it happens in the reaction, even though we cannot see it. Another term that's important is the collision view and the collision theory, and I will explain to you what the collision theory is as we proceed. So if we look at the submicro view of a reaction, let's say this is my representation for particle A, which is my reactant, and particle A converts and become a product, which is now particle B. And we use red for the reactant and blue for the product so that we can see what happens to the red particle during a reaction and where the blue particle comes into play and what happens to the blue particle as the reaction goes on. In front of us we have a closed vessel, meaning no gases can escape from here. And let's say we look at the reaction of A that converts into the product B, which is the blue product. So at the beginning, when our reaction starts, we can see in our closed vessel, we only have reactant, only red little particles. As we proceed here, we have more blues, and let's say at a time of 20 seconds, we have blue and red in your flask that's actually closed. And at this point, we will see that now we only, from the 1 mole of A, we only have 0.6 mole of A left. But in the meantime, some of that A converted into B. That's why we see the blue particles in between. And at a later stage, 40 seconds, regular time intervals, we can see that there's even a further change where I have 0.4 mole of A and 0.6 mole of B. At this stage, it might be the end of the reaction, but we can see at the end there is now more products than reactants. As I said, when we look at the microscopic view, what's happening at a level where we cannot see it with the naked eye? We call that the microscopic or the submicro view of this reaction. When we talk about collision theory, we know that all matter is made of particles, and that particles is in constant motion. That motion depends on the temperature. We know that if it's a high temperature, we've learned before, we know that the motion will be fast. At a low temperature, we know that the motion will be a lot longer. You need to have a collision between two particles for a reaction to happen. Now, at this point, I just want to say, if we look at collision collision, we can say it's a bumping of our particles, or we can say the particles hit each other, or the particles hit against the inside of your vessel. But if there's no bumping, or no hitting, or no collision, there will be no reaction taking place. The example that we have in front of us, we have hydrogen gas, where we see the bonds that reacts with oxygen gas. If this hydrogen and oxygen do not get in contact with each other, if they do not collide, nothing will happen, no water will form. But as soon as this hydrogen and the oxygen is placed in the same container, they will start to hit each other, they will collide, and they will then possibly go over into forming water, which is the product. But there is a temporary, unstable uphill, as we call it, period in this chemical reaction, and we call that the activated complex. It's got high energy at this complex. We call it energy hill because there's so much energy. So during that time, there's a bumping, but if that bumping or that collision is not a correct collision, we see that it will not form water. When we do have the collision taking place the right way, in the correct way that we need it to take place, we will see that after being in that unstable state, it will form the water molecules. So this brings us to the collision theory. Remember, all matter is made of particles, particles that moves, and that movement depends on the temperature. So the kinetic energy of the particles before the collision must be right. This is important. If that kinetic energy is a bit too high, if we have two atoms, we will see that that two atoms, the positive force from the nucleus, will start to repel each other. If that kinetic energy is too low, the electron clouds around the nucleus will start to repel each other. So too high, the positive and the positive will repel each other. Too low, the negative and the negative will repel each other. But if that happens, we say that the collision is unsuccessful. That collision that's unsuccessful will not ever result in a product. But when we have the kinetic energy of the particles, if it's just right, it will break the bonds between the reactants, and it will form new bonds for the products. And when that happens, we say that that is an effective collision. An effective collision will go over into forming product. So the rate of reaction is then determined by the number of effective collisions per unit time. You must bring in the per unit time. So for the last, I just want to say, for a reaction to be successful, for a reaction to produce product at the end, we need to look at the requirements. There must be a high number of collisions that take place. And that collisions, that particles must have a kinetic energy that is bigger or equal to the activation energy. If that happens, there might be product, but there's something else that we need. We need the correct orientation. In other words, if hydrogen and oxygen is now overlapping and your unpaired electrons overlap with their orbitals, we have just the correct orientation for it to happen. And that will lead to an effective collision. Now it's time for a break. Go and get revived and refreshed.